I think you were postdoc at King's College, and then we were both postdoc at University of Göttingen in Germany. Today, he will talk for us about the two-dimensional delta method and pairs of quadratic forms. Okay.
Well, thank you very much for the introduction. Thank you for the invitation to speak. Yeah, it's a pleasure to be addressing this audience, and it's a new audience for me. Um, so one thing, whoops, oh, me, just right. There we go. So one thing that I want, so there's a few preliminaries, right? And one preliminary that I want to draw your attention to is that there's going to be a bunch of notation, a bunch of symbols and definitions. And if you ever want to go back and see what I did earlier, so a copy of these slides is available online. So hopefully, if everything has worked, this should be available at tiny.cc/time-list. So that address is going to be in the bottom right of each slide. Okay, so you should freely be able to go back and hopefully this link still works. Okay, and my topic is going to be about Diophantine equations. So I'm going to talk to you about systems of polynomial equations with integer coefficients to be solved in integer variables. And in particular, I'm always going to be talking about systems of quadratic equations, basically. I think I probably never mention an equation that isn't a quadratic equation. This is just because otherwise there would be too much to talk about. So basically everything that I'm talking about, what either has been applied or one could try to apply it to some more general problem. But I'm just going to stick to systems of quadratic equations with integer coefficients and integer variables, just to keep the references manageable and so that we can state all our problems and theorems clearly. All right. So this up here is going to be our main object of study. So it's going to be a system of capital R homogeneous quadratic forms in S variables. So this condition S greater than 2R, this is for some technical reason. This is not particularly important. The point is that the number of variables is fairly large compared to the number of equations. So one thinks there should be solutions, right? If you have lots of variables and not so many equations, one thinks there should probably be solutions to the equations. And that's all that I'm saying here. So x1 up to xs is a vector of s integer variables, and vector f is a vector of r quadratic equations with integer coefficients in those integer variables. And then we're looking for solutions of f equals naught. So the system of polynomials equal to naught. Okay, I'm going to solve this with the variables being integers of size around b. So we're in some regime where we expect there to be lots of solutions, and we're going to look in particular for the solutions of size b. All right. And this fourth point is sort of more formally and precisely the thing that we're looking at. So I'm summing over all non-zero integer points, non-zero vectors of S integers, such that these R quadratic equations are satisfied. And we're looking at and we've got some weight function here. And this weight function you should think of as imposing the conditions that the solutions have size around b. So this w here is some function which vanishes unless x is no bigger than b, unless x lies in this, all the coordinates of x are no bigger than b. So we're definitely solving in integers of size at most b. And all of the other stuff, the fact that it's infinitely differentiable with integral one, this is some technical stuff. The important thing is that we're looking at integer solutions in integers of size at most b to a system of quadratic equations. Okay. So the question is, how many solutions should we expect? What size should we expect this counting function n to be? And so we can come up with a sort of a heuristic, a model, which gives us a guess as to what the answer ought to be. So the idea is that we're going to model our vector of integer variables by a vector of real numbers x. And so if we choose some random real numbers, the chance that this system of polynomials will be exactly equal to zero is zero. I mean, it's a very small subset of the real points where this equation is actually zero. So we're going to have a model of f of x, which is the integer part of f of these real variables. So we're going to choose, instead of a vector of integer variables, we're going to choose a random vector of real variables, and then we're going to round down every quadratic form to the next integer, and that's going to give us some vector of integers, which is going to be our model for the R quadratic forms f1 up to fr. Okay, so more precisely what I mean by this, so to repeat myself, but a little more carefully, we're going to define a random variable, x, taking values in, so this random variable takes values in r to the s, and its probability density function is this b to the minus s w of the variable divided by b. So this condition that we had earlier, that w has integral 1, ensures that this thing is a valid random variable. So we're choosing our vector of real variables at random according to this weight w. So the probability that x takes a particular value is proportional to this weight w. And then we guess that maybe the probability of this sum here is like choosing having two b shots at getting this random variable to equal 0. So we take 2b to the s copies of this random variable, corresponding to having about 2b to the s terms in this sum, and then we take the for each term in the sum, we take the probability that our random model is equal to 0. So the probability that the integer part of f is 0 is the probability that each component of f lies between 0 and 1. And then one can work out what this probability is, and one concludes that one can write it as a volume. You can't give a nice explicit formula, but you can write it as a volume, and in that way you conclude that this random model is predicting that we have around b to the s minus 2r solutions. So the number of solutions in integers of size up to b should be about b to the s minus 2r times some constant. Okay. And so this was the reason for having more than 2r variables in the first place. This means that our random model predicts we should have lots of solutions. So this parameter b, one should think of as large, it's tending to infinity. And so this is predicting that there are lots of solutions when we look at large integers.
So the randomness is on sampling of the points, right? It's not on the equations. If you vary equations, would you get something out of that too?
So that's correct. So people do also look at, so I've been saying things like typically, and we want to understand this function. And certainly something you could say is maybe we should choose a random system of equations and ask how the random system of equations works. And that's not going to be the perspective that I take. although people certainly have and do. I'm going to look at a fixed system of equations and then count the number of solutions to that fixed system of equations. So this is a random model for a fixed system of quadratic equations. Yeah, thank you for the question. Okay. So this random model sometimes gives an answer which is completely wrong. So for example, if we take this, so r equals 1, we're taking a single quadratic form. We take the quadratic form x squared plus y squared minus 3z squared. So this has no non-zero integer solutions. And the reason is that, so one can look mod 3, one can reduce modulo 3, and one finds that in order for f to equal 0, this vector of variables has to be congruent to 0 mod 3. And you divide it by 3, and you keep going, and you conclude that the vector of variables you started with must have been 0 all along. So there's some argument by descent, which shows that we have no non-zero solutions to this equation in integers. And in this case, there are 3 variables and 1 equation. So here, s minus 2r is 1. And so we would expect this thing to have size around b. So in fact, this, yeah, if one runs this probabilistic heuristic, it does predict that the number of solutions should be some positive constant times b, and it's not, it's 0. And the solution is, so the reason that this didn't work was that we had some obstruction mod 3, x, the vector of variables all had to be divisible by 3. And so we need to look mod 3 to understand this equation. And so what one can do is one can construct a version of this random model for each prime p. And that gives one some kind of correction factor, which one should use to adjust the heuristic that I described. So, I'm not going to go through the construction, but there is a version of exactly the kind of random variable heuristic that I described, mod actually p to the n for each prime power p to the n, and that gives one some kind of correction factor that one should multiply this prediction by. And in the case of this counterexample here, that correction factor is 0. So in the case of this equation, once we have this product of correction factors for each prime, then this heuristic correctly predicts that this equation should have no non-zero solutions. This product will be 0. Okay. And to be, without going into all the details, the way one does this is, so here so one can think of this xp here as being uniformly distributed. I've been fancy and said it's uniformly distributed on the p-adic integers, but one can perfectly well think of this as being uniformly distributed on z mod p to the nz to the s. So this is some random model. F of xp is some random model where we choose the variables to be random integers mod p to the n. And then we look at the probability that this random model is equal to 0 mod p to the n. This gives one, so this gives one some correction factor that one should use to adjust the heuristic. and then one gets here some probability that the real model is has a solution, that the real model gives a solution, and here there's some product of probabilities that the mod P model gives a solution. So this this heuristic is called by many names. So this is an example of a circle method heuristic. People also say heuristic circle method, or Hardy-Littlewood heuristic, or Hardy-Littlewood asymptotic. It goes by many names, but it's just some kind of not completely naive prediction for how many solutions you should have. And in my branch of analytic number theory, the people are so familiar with this that sometimes they don't really think about why it's true. But okay, there's some kind of probabilistic justification underneath there. Okay. So is this actually true? So I've got again this vector of this system of quadratic forms, and I've got this this prediction for how many solutions they should have in integers of height around b. So in this talk, I call this thing the quantitative Hasse principle. Like I say, it has many names, so we have, and so at this point I should, so I've already used some of this notation and I should make sure I've defined it all. So I'm going to use big O and Vinogradov notation in this talk. So A is big O of B, which is also written A is less than B, just means that the absolute value of A is bounded by a constant times B. So it says A is more or less the size of B, at least as far as upper bounds are concerned. And this frowny smiley face is when A is big O of B and B is big O of A. In other words, they have about the same size. And this twiddles for me is going to be when these are asymptotically equivalent. So when their ratio tends to 1, the parameter that tends to infinity is always going to be B. And A is little o of B means their ratio tends to 0. In other words, A is much smaller than B. And so in my statement of the quantitative Hasse principle up here, on the right-hand side was, so this part here is my heuristic prediction for how large this, this number of solutions should be. And it's multiplied here by a factor which is 1 plus little o of 1. In other words, a factor which tends to 1 as b tends to infinity. So that these two sides are, this is a fancy way of saying that the number of solutions is asymptotically equivalent to the prediction, unless the prediction is 0, in which case the number of solutions should also be 0. Okay. Yes, so I have a brief discussion here about the name quantitative Hasse principle for this kind of prediction for the number of solutions we should have. The idea here is that there's something called the smooth Hasse principle, which says essentially that if the right-hand side in this prediction is non-zero, then the left-hand side is non-zero. That's slightly normally the smooth Hasse principle is stated in a slightly different way to this, but the idea here is one can think of it as just saying that if one side of this conjecture is non-zero, then the other side should also be non-zero. So it's something that is strictly weaker than the quantitative Hasse principle. And this is something called the Minkowski-Hasse theorem. So if you have a single quadratic form, and it has solutions modulo p to the n. If you have a single homogeneous quadratic equation, and it has solutions modulo p to the n for every n, and it has real solutions, then it will have integer solutions. So this is the original example of the Hasse principle. Okay, and this so this thing is not always true. So this quantitative Hasse principle is a conjecture, and moreover, it's not a correct conjecture. It's not always the case that these two things are asymptotically equivalent. So in particular, if the number of forms is fairly small and the number of variables is fairly small, we know lots of counterexamples. So a nice one is, so if we have a single quadratic form in 3 or 4 variables, so in that case, the number of variables is bigger than 2r. So this prediction does make sense. It is predicting that there are lots of solutions. And the Hasse principle even holds, but it turns out that this prediction for the number of solutions is incorrect. And roughly speaking, the reason, or part of the reason, is that this product diverges, and so the prediction turns out not to make as much sense as one might hope, and one has to sort of renormalize things, and some extra factors of log B appear. Okay. So, I mean, if S is 3, then it's not quite like that, but the general idea is that there are some extra factors of log B that you need to put in order for everything to make sense. There's also an interesting example of 2 quadratic forms in 5 variables, for which this thing is not correct. And this is due to something called the Brauer-Manin obstruction. So basically, there can be some sort of more interesting and complicated arithmetic in those cases with only a small number of variables. Okay, but in general, in particular, if the number of variables is sufficiently large, then we do expect this quantitative Hasse principle to be true. At least if the number of variables is sufficiently large and the system of forms F is sufficiently nice. So let me say something more about that. Okay, so this is what's known as regards the smooth Hasse principle. So as I said, for a single quadratic form, when R is 1, then the smooth Hasse principle always holds. I've said Hasse principle, but I should really be saying here smooth Hasse principle. So this is that one side of this conjecture is non-zero if and only if the other side is. So when we have a single quadratic form, it's a classical theorem of Hasse and Minkowski. And when we have 2 quadratic forms, there's actually been some interesting, very recent work of Alexander Molyakov, which improves a result of Heath Brown. So the smooth Hasse principle holds if you have at least 8 variables for a pair of quadratic forms. So before Molyakov's result, there was this condition that the system of 2 quadratic forms had to be smooth. So what this means is defined at the bottom of my slide here. So it means that this system of equations f of x equals 0 defines a smooth complex manifold except at the origin. So this is one way to say it. It means that the zero locus of this system of equations is smooth except at the origin, even when you consider all the complex solutions. Okay. So with three quadratic forms, we have another result of Heath-Brown, which says that the smooth Hasse principle holds if we have at least 19 variables. So this is growing quite fast. I mean, for one quadratic form, I was talking on the last slide about the cases of 3 and 4 variables. For two quadratic forms, I was talking on the last slide about the case of 5 variables, and now about 8 variables. And it seems to be growing very fast, right? It's more than doubled to get the amount of variables we need to get a theorem has more than doubled when we go up to 3 variables. So, this kind of suggests that this problem is getting quite difficult as the number of forms increases. Okay, so the quantitative Hasse principle, this estimate for the number of solutions, so this is known if we have a few more variables, then this is usually more variables than we need just for the Hasse principle. There are also results about this. So again, all of these theorems, these are about this asymptotic here. It's about when we have this asymptotic prediction for the number of solutions of bounded height in integers to a system of quadratic equations. If we have a single quadratic equation, there are really a very large number of different ways to try to prove this asymptotic. The Hardy-Littlewood circle method, which was not exactly invented by Hardy and Littlewood in its modern form, it was kind of written down by Wiener-Gronow, and it has its origins in work of Ramanujan, but it's conventionally called the Hardy-Littlewood circle method. This works for 5 or more variables. Oops, sorry. And there are lots of other, if you only have a single quadratic form, there are lots of other ways you could try to estimate the number of integer zeros of that quadratic form. So you could try to do it with zeta functions. You could try to do it with the geometry of numbers. You could try to do it with ergodic theory. And there are authors taking all of these various approaches. So some of them are in these references here. And in general, so the sort of most general single result that we have is due to Brian Birch. So this is a result from 1962, which uses again this Hardy-Littlewood circle method, and I'll tell you more about that later. It uses this Hardy-Littlewood circle method to handle the case when the number of variables is at least twice r times r plus 1 plus r. So this is the case when, again, f is smooth. So we're looking at the case when the system of equations f equals 0 defines a non-singular complex manifold away from the origin. So in that case, the circle method works well. Birch was able to get a result, was able to prove this asymptotic, that is, as long as the number of variables is at least this quadratic polynomial in the number of forms. So again, f is a fixed system of homogeneous quadratic equations, and as long as it's smooth and the number of variables is larger than this quadratic polynomial in the number of forms, then we're getting a result. Okay, and so it took a while for there to be on this particular problem with systems of quadratic forms, it took a while to see progress beyond Birch's work. So there was actually a very long period where, although Birch's work had been strengthened and generalized in lots and lots of other directions, this problem with systems of quadratic forms didn't really see progress. But eventually it did. So that's substantially due to the work of Heath Brown in '96, where he introduced what is now often called the delta method. So this is based on ideas originally due to Duke, Friedlander, and Iwaniec. And Heath Brown reframed it as a version of the circle method. And we'll talk more about what that means later. But by looking at the work, by looking at the method of Duke, Friedlander, and Iwaniec through the lens of the circle method, by understanding it as a version of the circle method, Heath Brown was able to treat, using the circle method, the case of a single form in 3 or more variables. So this includes cases when the statement that I gave earlier is not quite right. So it includes cases in which the problem is very difficult. These cases were understood by other methods, but this was the first time that they'd been treated with the circle method. And the introduction of the delta method kind of completely changed the limits of what the circle method could do, and led to a lot of further work on this kind of problem. So in 2013 and 14, Browning and Munchley were able to look. So this is a slightly elaborate looking definition. So what I'm saying here, so F, remember, is a vector of quadratic forms. And so what I'm saying here is that F1 of X is X1 squared plus X2 squared plus maybe I'll F superscript 2, 1, X3 up to XS. And yeah, maybe actually it goes downstairs, maybe F 2, 1. And then F2 of X is equal to F2, 2 of X3 up to XS. My S's look a bit like 5s. Okay, so in other words, what we're saying is that the first 2 variables only appear in the first quadratic form. So we've got 2 quadratic forms, F1 and F2. And my claim is that my hypothesis here, or the hypothesis of Browning and Munchley here, is that the first 2 variables, X1 and X2, they only appear in the first form, F1, and they appear in exactly this way, as a term X squared plus Y squared, and then some terms that don't involve the X1 and X2 variables at all. So this F21 is some quadratic form in the remaining variables. And then the second quadratic form, F2, doesn't depend at all on the first 2 variables, X1 and X2. So in other words, this system of 2 quadratic forms has very, very nice and very restricted dependence on the first 2 variables. And so this is a slightly technical looking case, although it does have a geometric interpretation. And the reason, and you know, this case was, it turned out that in this case, it's particularly easy to apply the delta method. And so this was the first system of 2 quadratic forms that was treated by the delta method, and the first reasonably general system of multiple quadratic forms that was treated by the circle method since the work of Birch. Okay, so this was even though it looks technical, this was a big step forward, and it was followed by lots and lots of other work. So Muntli went on to, as long as there are at least 11 variables, handle any system of any smooth system of 2 quadratic forms in 11 variables. So again, what we're doing here, all of these results are proving the quantitative Hasse principle and proving an asymptotic for this number of zeros of f in integer variables of size around b. So an estimate for the number of integer zeros of the system of quadratic forms in integers of known size. Okay, and so under some slightly different technical hypotheses, Heath, Brown, and Pearce were able to reduce that 11 variables to 10 variables. So this is under the hypothesis that the system of 2 quadratic forms is the sum of 2 vectors of quadratic forms, one that only depends on the first 5 variables and one that only depends on the second 5 variables. So again, a technical assumption which lets you reduce the number of variables needed by 1. The number of variables that you need is kind of the game in this area. So the number of variables that Birch needs for a smooth system of 2 quadratic forms is 14. And so getting a result with fewer than 14 variables is interesting, is the idea here. Okay, and then there are two other results that I want to mention that are more recent. So I haven't quite put these in chronological order. So one is so the work of Browning and Muntli, actually my student Nuno Arala, recently slightly weakened this technical condition. So instead of a sum of 2 squares here, you can put a general positive definite quadratic form. And it turns out that this is maybe more technical than one might expect. It turns out that the structure of the binary quadratic form x squared plus y squared was really being used in this proof. And it turns out that some interesting technical complexities arise when you try to do this. Okay. Another interesting point is, so the best number of variables occurring here is 9. So there's an 8 in quotes. And as some people might even have guessed, this 8 variables is under GRH. And also, oh no, this H is not under GRH. Sorry, this H is not under GRH. This H is for very special forms F. Pardon me. Yes. So okay. The best number of variables here occurring here is 9. There is this 8, which you can get for very, very special systems of forms F, which are really very restricted systems of forms F. So the best number of variables that applies to any reasonable class of quadratic forms is 9. And over function fields, so I'm not going to write down exactly what this means, but if you replace the integers by polynomials in one variable with coefficients in a finite field, then you can actually solve the equivalent problem and prove the equivalent asymptotic as long as you have 9 variables. So in fact, this very restricted case, this technical hypothesis that the forms have to have this special shape, you can replace it by the natural hypothesis that the forms are smooth over this function field. So this suggests that it ought to be possible in Muntli's result, which requires 11 variables. This kind of suggests that maybe it should be possible to replace this 11 variables with 9 variables. And one might think a bit more about it and conclude that actually maybe to reduce this 11 to 9, one should assume the Riemann hypothesis, because over function fields, we know the Riemann hypothesis. So in function fields of positive characteristic, we know the Riemann hypothesis. And so maybe to make it a fair competition, one should be allowed to assume the Riemann hypothesis if you want to prove this asymptotic formula for systems of 2 quadratic forms in 9 variables. Okay, so so that's a long list of results, and the main takeaway that I want to get out of this is that in recent years, in the last 20 years, there's been a bit of a flurry of activity as the implications of this delta method has sunk in, and people have tried lots of different shapes of quadratic forms and lots of different assumptions in an attempt to get the number of variables that you need in Birch's theorem a bit lower. That's the takeaway here. So I also should at least put on the screen a few more results of this character for a larger number of forms. So I'm not going to go into any detail here, but you can do 20 variables for suitably special so-called split systems of 3 quadratic forms. You need 9 R variables in general now. So this is a previous result of mine. So this improves Birch's result for systems of 4 or more forms. And this is under the natural condition that the system of forms is smooth. And for some special systems, one can go as low as 6 R variables, which is considered pretty impressive. And this is some very interesting work of Browning, Pearce, and Schindler. So there has been a little bit of work on systems of more than 2 forms, but not quite as much. It seems to be a little bit harder. So the main takeaway is just that people have tried lots of different technical assumptions on the forms, on the quadratic equations, in order to try to apply Heath-Brown's delta method to systems of 2 quadratic equations. Okay, so here again is the statement of the quantitative Hasse principle, for those who have missed it, and now the statement of the result that with a few minutes left to talk about it. This is the statement of the result that I'm actually here to discuss today. So this is joint with Junshan Li and Pankaj Vishay of forgot the name of the university. What's the university that's near Sacramento? UC Davis, and University of Durham. Okay, good. And so what we do is we take this previous work of Vichy, which solved the equivalent problem over in positive characteristic over function fields and over this function field FQT. And we try to do a version of this for the original problem of 2 quadratic equations to be solved in integers. And we're able to get what we feel is kind of a fair analog. So we can prove this asymptotic for systems of 2 homogeneous quadratic equations with integer coefficients, as long as the system is smooth and the number of variables is at least 10. And if we assume GRH, then we can get that number of variables down to 9. So that's sort of what one might hope for as an equivalent result. So it's done first by Vichy in the function field case, and we have a sort of imitation or an analog of his method in this case. And so we reduce this 14, which was reduced to 11 by Muntli, we reduce it by 1 more down to 10. And on GRH, we can reduce it by 2 down to 9. Okay.
There's a question in the comments. So could you please remind us with the Artin conjecture for comparison?
So I'm not actually sure which conjecture that is. So this is maybe existence of
it's the Artin Lang improved or generalized these for comparing the number, systems, homogeneous systems.
Okay,
so number of variables versus the number of equations.
So this would be maybe over finite fields?
No. It's over number fields.
So I'm afraid,
for instance, it generalizes Minkowski, for instance, for one quadratic form. And more generally, if it's forms of higher degree as well, but here you're specializing to systems of quadratic forms. Okay, forget it if you don't remember. I don't remember it.
So this is an interesting reference point, which I'll look up later. So is this a conjecture about which guarantees existence of integer zeros, or which guarantees existence?
Well, it's rational, but if you're dealing with homogeneous, it's equivalent to talk about rational.
Okay, I will look this up. I guess this. So my guess is that this is probably probably just asking for existence of solutions.
Correct.
And not for a count. And it is
Correct.
true I'm a bit ignorant about this because I'm a bit hyper-focused on getting an estimate for the number of them. So I think this is an interesting point that I should look into. So I guess the backdrop here is kind of that probably whatever the number of variables that are required for the Artin-Lang conjecture to make sense, it's probably rather smaller than the number of variables you would need even in the best possible case for the circle method to work. So probably this is a conjecture about a regime in which you do not expect the quantitative Hasse principle to hold. That would be my guess. Or alternatively, it might be a conjecture that relates quite heavily to whether or not you're guaranteed to have p-adic solutions for every p. And in that case, it might actually involve more variables. So yeah, this is an interesting point of comparison, which it's a good point. I'll look into it. So thank you. So this is where we stand. And I think what I'd like to do is just say a few words about the proof. This is proved by the circle method, or by a version of the circle method. And something that was very interesting to me in this project is that it kind of made me think a lot about what the circle method really is. So people say that results are proved by the circle method, but it's not really the case that you can find one textbook which teaches you like a circle method, and then every application of the circle method can be understood in the terms you learned in the textbook. There are lots of different things that are called the circle method. So this project made me think a lot about what those ideas really have in common. So just in a few minutes then at the end, the idea of the circle method is that we encode our system of forms f using an exponential sum. So we have this notation E of t is e to the 2 pi I t. And then what we do is we sum over all integer points, so not necessarily the ones at which f vanishes, but all of them. And we look at e to the 2 pi alpha dot f of x. So in other words, e to the 2 pi I sum alpha I f I of x. Then we sum this with this smooth weight, which appears basically for technical reasons. So okay, Mr. 1 here, never mind. So because the integral of e to the 2 pi I n t from t is 0 to 1 is 0 or 1, depending on whether n is 0 or not. So if n is a non-zero integer, then this is 0, and if n is 0, then this is 1. So this identity, which is kind of basic calculus and trigonometry, means that we can express our counting function, our number of zeros, as an integral of this exponential sum. And this is just a trivial thing. This is just a trivial identity and doesn't tell you anything. And the circle method happens when one combines this trivial identity with a nice decomposition of this unit hypercube that you're integrating over. A nice decomposition maybe means a partition of unity supported on this hypercube, if that's your terminology. So the classical partition of unity to use is the so-called fairy dissection, which takes the unit interval 0, 1 and partitions it into these little arcs, which is these are small arcs or small intervals, conventionally called arcs. And this is a small interval containing the rational number a over q. It's a naturally defined small interval containing the number a over q. And then we break up the whole of the interval 0, 1 into a disjoint union of these intervals, where a over q runs over all rational numbers with denominator up to q lying in this interval. So this is the class, and it turns out that on such an interval, a small interval around around a rational number a over q, you have very nice estimates for an exponential sum like this. On such an interval, you can estimate such an exponential sum. And really the whole story of how we got this result is a story of trying to choose the right decomposition, or actually the right partition of unity supported on this 0, 1. And so that's something that you can if you want to see that, you can go to the online version of these slides, and you can scroll down past the point that I've gone to today, and I talk more about what decomposition we actually use. So I will leave it there. Thank you.